Good afternoon, good evening, everyone. So, welcome to week 12 of problem solving session for analog communication network NPTEL course. So, today we will be mostly dealing with internet protocol. So, it is not a problem solving session per se because it's a highly theoretical subject, but we will try to see what are the basic concepts and then we will solve some problems based on that. But today mostly it will be a theoretical session as the topic in itself is pretty theoretical. So today's topic is Internet Protocol and TCP/IP. So today we will be not dealing with physical layer or any lower layer. We will be dealing with the network layer. So here comes the Internet Protocol. So we have dealt with physical layer and data link layer. Now we will simply go to network layer. So network layer has TCP/IP protocol. So the first section will be IPv4. IPv4 means the IP protocol that we know that contains 4-digit, like 4-number IP addresses. Like we have 10.197.63.2 like that. So that is the IPv4, the typical IP addresses you see everywhere. Then there is another protocol which is ICMPv4, which is auxiliary protocol used to help IPv4. And then there will be 1 minute. Yeah. Uh, yeah. And then finally there will be third section which is mobile IP. So IPv4 is IP protocol that resides in the network layer. So the physical layer and data link layer has been discussed previously in the previous weeks. So now we will discuss IPv4. Now IPv4 is a packet delivery service. So it creates addresses for all computers that are connected to a particular network, and then it gives its best effort to transmit a particular packet from its source to its destination. So it is a best effort protocol, means it will try its best to deliver the packets, but there is simply no guarantee that the packet will reach in its intact form to the receiver. It might get corrupted, it might get lost, it might arrive out of order, etc. So IPv4 is a connectionless protocol that uses the datagram approach. That means the addresses of the sender and receiver are not connected, like the sender and receiver not physically or virtually connected to each other. So there is no connection. Instead, the source has the destination address, and then the packet tries to find the best possible route to the destination address. So so here that's why it is best effort, because it might take a long route, it might get corrupted, and since there is no dedicated connection, so there can be no guarantee of the quality of communication. So the IPv4 packets are called datagrams. So the datagrams have around 20, the data IP datagram, it can be around 20, starting from 20 to ending at 65,535 bytes, which is like the maximum if all the bits are turned on. If all the bits are 1, that is the maximum number of bytes that it can store. So there, out of this 20 to 65,000 bytes, 20 to 60 bytes, the first 20 to 60 bytes are used as headers. So in this header there are multiple bytes that are reserved for multiple purposes. 0 to 4 is the first is the version number header, and then there is the header length byte, which version number will specify, of course, whether it is IPv4 or there is a competing technology called IPv6 which uses hexadecimal numbering and has 6 zones or 6 decimal numbers. the 6 hexadecimal numbers. So IPv4 has uh, so IPv4 has four separate four decimal separated, rather dot separated decimal numbers while the competing technology is IPv6, while IPv6 has 6 dot separated hexadecimal numbers. So 10.192.33.1, this can be IPv4, whereas 1A dot 55 dot 29 dot 1 dot f1 dot 1 2, like that, 1 2 3 4 5 dot 0 1, this can be IPv6. So IPv6 has 6 hexadecimal numbers, whereas IPv4 has 10 decimal numbers. So for 10 decimal numbers, each number in IPv4 can go from 0 to 255. Now what is 0 to 255? Why is 255 special? Well, so why is 255 special? Because 255 is 8 ones. So it is 0 0 0 0 0 0 0 0 to 1 1 1 1 1 1 1. So this is 255 ones. So 255, that is all ones, and it is 8 digits. So 8 digit means 1 byte. So each decimal number is 1 byte. So if each decimal number is 1 byte, means 8 bits, then what is the maximum decimal number you can store? It is 1 byte is this 255. So 1 byte, 1 byte, 1 byte, 1 byte. So 4 bytes. So IPv4 address takes IPv4 address needs 4 bytes. Now let's go back to the protocol bracket. So first is VER. VER is 4 bits, not bytes, bits, and half a byte. So it's just half a byte. This half a byte will dictate what version you are using, IPv4 or IPv6. Then there is HLEN. HLEN means this one will give you the header length. So this is 20 to 60 bytes. So the header is variable in nature, but the packet has to know reliably what is the length of this. So the packet has to know reliably what is the length of the header, where header ends and where payload starts. So hlab will dictate where header ends and where payload starts. Next is service type, and then there is total length. Service type we will come back to later. And then there is total length. Total length is basically the total header plus payload. What is the length? Since both the header length and the payload length is variable, so you need to specify what is the header length and what is the total length. And then there is identification, flags, fragmentation effect. So we'll come back to that one by one. So first is service type. So we have understood what is version number and header length. Next is service type. In the original design of IP header, this field was referred to as type of service, which defined the datagram should be handled. So in this way, you can see that this datagram may be a message, it may be a control signal, it may be an information signal. So control signal has instructions to execute, message signal has messages from the sender, whereas what else? This packet length, message, and then there may be information. So in information packets you get the information about the sender, so it wants to give some critical information about its status, then it might send the information. So the type of service will be decided here in service type. Then there is total length. Total length defines of the IP datagram in bytes. So a 16-bit number. So here the total length packet, total length has been allocated 16 bits. So if you turn on 16 bits, all one, then you get 65,535. So 16 ones in binary is 65,535 in decimal. So that's why you only have 65,535 possible addresses. Now 65 the I6 a 16-bit number can have. So size, but usually since the total length can be more than, cannot be more than 65,535, but usually the size of datagram is much less than this. So after this, so why do we need this field? Because the packet has to know, the sender and receiver both has to know the exact length of the packet, without which it might not end when packet starts and when one packet starts and when another packet ends, because all the packets are kind of in a bit stream. From the physical layer point of view, they are in a bit stream, so you have to know the total length in order to distinguish the bit stream. Now we have identification, flag, and fragmentation offset. These three fields are related to the fragmentation of IP datagram when size of datagram is larger than the underlying network can carry. So these three are used to fragment the datagram if the datagram length is larger than the total length of datagram that the system it is hosted in can handle. So even though you can make 65,535 byte long datagrams, theoretically, but the problem is that the systems that are hosting these addresses may not be equipped to handle this particularly long datagram. So what might happen is they might cut it short somewhere. So if it is cut short somewhere, then it is divided into multiple packets because the system is not able to handle. So that is identification, flag, and fragmentation offset. Next is time to live. Time to live is basically the time that the packet has been live on the system. So the time for which the datagram has been live in the system. So once it reaches a router, this TTL is reset to 0, and then it starts decreasing with time. And when a maximum time elapses, then basically the datagram has been live on the datagram has been live on the system for too long without processing. So we cannot afford that. We cannot let a datagram which is not getting processed hog the resources. So there is a time to live, and when this time to live counter, so every packet is given a maximum time to live. If this time to live counter decrements to 0, so say the packet is assigned that it can live for 30 seconds. So it will start a reverse countdown 30, 29, 28, 27 till it reaches the next router or the timer runs out. If the timer runs out, then the packet is discarded. And then protocol. So this protocol is the so this protocol specifies the transport layer protocol, that is TCP/IP or UDP. So the protocol that the packets will be processed in a particular way for a particular protocol. So we have to be very specific which protocol we are using. And that is specified in the protocol field. Now after the protocol field, we have time to live protocol, then header checksum. So next we have header checksum. So IP is not a reliable protocol, as we have discussed previously. IP is a best effort protocol, not a guaranteed protocol. So it does not have any guaranteed delivery. It tries its best, but it may or may not reach the receiver in a perfectly accurate form. So IP is not a reliable protocol. It does not check whether the payload carried by a datagram is corrupted during transmission. IP puts the burden of error checking of the payload on the protocol that owns the payload, such as UDP or TCP. So again, UDP, TCP are transport layer protocol, whereas IP is a network layer protocol. So this error correction, the network layer protocol, which is a more universal and simple protocol, this it does not do any kind of error checking. Instead, it passes on the function of error checking to the transport layer protocol, that is UDP or TCP. Now the datagram header, however, is added by IP, and its error checking is the responsibility of IP. So the payload is not being checked by the datagram. The payload is not being checked by the IP. So even if you send a wrong even if you send a wrong packet, it will even if you send a wrong data in payload, it will pass it on. But what it does do an error checking on is the header, because the header has been put there by the IP, so it is the responsibility of the IP. So the to ensure that the correct header is getting transmitted, what it does is it creates a checksum, and this checksum is then checked at the end of the end for the corruption, for to check whether the header is corrupted or not. So how does checksum happen? Checksum basically goes through, basically you process all the bits. So you process all the bits through an algorithm through all the header bits. This will generate a checksum. So at sender, what I will do is, at sender we will create the algorithm header checksum, and then this checksum at receiver will be compared with the received bits. At receiver, compare algorithm received header bits checksum. So the checksum is prepared at the transmitter, and at the receiver you again pass the same algorithm that was used to prepare the checksum for the received header bits, and you compare it with the checksum. But the problem here is that we can often have the same output for received header bits passed through the algorithm and checksum. So received header bits passing through algorithm may be equal to checksum even if the received header bits is different from the transmitted header bits. So that is one problem. And then there is a second problem, that is that this checksum itself might get corrupted. So then we can, even if we transmit all the bits correctly, if the other bits correctly, if the checksum gets corrupted, then you might have a problem in your hands. So with these two in mind, we have to think of some other algorithm. But for now, this checks, because as I said, so for error checking we have to do something more sophisticated than checksum. But IP address is a very IP protocol is a very simple protocol. So here we can stick with checksum and we can carry on. And for the payload we can have other sophisticated algorithms. So to demonstrate checksum, I will show. Say you have header bits as, so there are 20 bytes of header in IRP datagram. Of course we cannot write 20 bytes here, so I will take a small header example. So example is, say you transmit 11001010. This is transmitted, so for checksum you can just add the digits. So checksum is 1 plus 1 2 plus 1 3 plus 1 4. Checksum is equal to 4, and 4 you can write as 0. You can write as 0 1 0 0. Let's not focus too much on that. So here checksum. Next, let's say we receive 1100 1110. So the received sum is 5, which is not equal to checksum. Hence we can conclude that we have an error in the transmission. Next, after header checksum, we have source and destination addresses. So these are simply the 4 byte or 32-bit addresses. So you need 448 bytes of addresses. So 32 bytes, 32 bits. So you have 32 bits of source address and 32 bits of destination address. Next, we have options. So options is just not required. So options are optional features. So they are not required exactly. But for added processing, we can supply them. So this all implementations may not have them. So you have to be sure that these optional features are implemented in all the package systems through which this packet will go. So it is something added, you can say added service. হ্যালো। হ্যাঁ, ক্লাস নিচ্ছিলাম, কি হয়েছে? তোমার ইচ্ছা গো, আমি জানি না। 1000 1200 টাকা লাগে তো, এবার তোমার ইচ্ছা, তুমি রিপেয়ার করবে কি করবে না। 800 টাকা নট নেসেসারি, 800 টাকায় হয়তো পিজিএন পাবে, আর একটু বেটার গুলো 1200 1300 টাকাও হয়। না আমি জানি না, 800 টাকায় কিনেছি, কে বললো তোমার? দাঁড়াও, আমি কিন্তু সেরকম বলিনি, আমি দাঁড়াও একটু সেকশন প্রাইস বুঝতে দাও। তোমার আসলে এক এক সময় না অন্যের কাজ না বুঝে তোমার হেল্প করতে হয়। অন্যের কাজটা কোনো কাজই নয়, খালি তোমার কাজটাই কাজ। দাঁড়া, হ্যাঁ 800 টাকায় পেয়ে যাবে। আমি কি বললাম, অন্যের কাজটাও কাজ। রাখো। So next is options, as we have seen that options are optional features that have can be implemented based on whatever the whatever the implementation is in the network devices. And next we have payload. Payload is just the data that has been sent. So there is not much that is done with the payload in the IP protocol. So and next you can see there is some problems, like in IPv4 packet the value of HLAN is 1000. How many bytes of options are being carried in the packet? So So the value of hlen is 1000. How many bytes of options are being carried? Hlen being 1000 means there are 8 bytes of header. So there are 8 bytes of header. Now 8 byte means 32 bits. Now the base header without any options is base header without any options is 20 bits. Now header length is 1000 binary, that is 8 bytes, that is 32 bit. So next is in an IPv4 packet the hlen is 5 and the value of total length is 28 hexadecimal. So how many bytes of data are being carried? So the value of hlen is 5 and total length field is 28 hexadecimal. So you can take 2 minutes to try this out. In an IPv4 packet, the value of hlen, that is header length, is 5 and the value of total length field is 28 hexadecimal. So you have to convert both of these to decimals and then compare the number of bits. So how many bytes of data are being carried by this packet? So data means here payload. So you have to find the header length, you have to find the total length, then you can get the payload. So here the value of header length is 5. So len is 5. Header length is 5 bytes, while total length is 0028 hexadecimal. Is equal to 2 into 16 plus 8, so that is 40 bytes. Thus the datagram carries 40 minus 5 is equal to 35 bytes of payload. So it carries 35 bytes. Next, okay, here the len or header length, so header length has to be multiplied by 4. So there is a small mistake. So header length has to be multiplied by 4. So header length is len into 4. So this is 5 into 4 equal to 20 bytes. So it carries 40 minus 20 equal to 20 bytes of payload. So you just have to multiply the len by 4. The header length can be found by multiplying the value of len field by 4. So this sorts that. Now once we know the header length, we can minus that from the total length to get the payload length. So next problem is an IPv4 packet has arrived with first few hexadecimal digits. So hexadecimal digits, each hexadecimal digit takes around 4 into 6. So each hexadecimal digit can be maximum f. F means 50. 15 is 1, 1, 1, 1. So each hexadecimal digit takes 4 bits. So each hexadecimal has 4 bits. How many hop can this packet travel before being dropped? So to find the time to live, we skip 8 bytes. The time to live field is 9th byte. So we have to find the time to live. So this is a IPv4 packet. So here there is a time to live information embedded. Now each hexadecimal digit is worth half a byte. One hexadecimal digit is 4 bits or half a byte. One hexadecimal digit 4 bits equal to 0.5 bytes. So each hexadecimal digit is worth half a byte. Now, what is the position for time to live field? The time to live field is at 4 plus 4a 31 32, so 32 6, and this is 32 64, so we have to bypass 64 bits. So time to live starts from the 65th bit, so we have to bypass 64 bits. 64 bits means 8 bytes. Now each hexadecimal, two hexadecimal digits make 1 byte, so to skip 8 bytes we have to skip 16 hexadecimal digits. So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So after that we need 1 byte, so that 1 byte is 0 1. So time to live field is 0 1 hexadecimal. So 0 1 hexadecimal means it can travel only 1 hop. Next is fragmentation. Fragmentation means that the datagram might be too long for a particular packet on which a particular system on which it travels to. So if it is too long for a particular system, then what will happen is that it will readjust itself by fragmenting into smaller pieces, and this, the format and size of the sent frame will depend on the protocol used by the physical network through which the frame is going to travel. So yeah, the way it will be fragmented will be dictated by the protocol which is fragmenting it. I think fragmentation is not included in the syllabus, so Now we will go to something else, that is IP addressing. So next we'll go to IP addressing rather than going into fragmentation. We'll go into the types of IP addresses. Now we will go to our next topic, that is ARP. So ARP is a data link protocol. So the next issue is ARP. So even if we have IP addresses in a connectionless network such as the internet, we cannot make a datagram reach its destination by using only IP addresses. The reason is that each datagram in the internet from the same host to source host to same destination host may take a different path. So each datagram that goes from same source to same destination. Class teacher.
ম্যাডামের আন্ডারে যে কাজ করেছে অঙ্কিত আছে না, অঙ্কিত পটনায়ক, ও কি আছে আজকে?
হ্যাঁ, সকালে ছিল।
এখন আছে কি? ম্যাডাম একটু দেখা করতে বললেন।
চলে গেছে, তুমি কল করে আসলে ক্লাস
ঠিক আছে, আমি বলে দিই।
That IP addresses, so even if we are sending multiple packets from one source to one destination, the packets might take different routes to reach the final destination. Thus we cannot have Thus, we cannot have only IP addresses to deliver packets from source to destination. Now, we need to remember that IP addresses in a datagram cannot be changed. If the destination IP address in a datagram changes, the packet never reaches its destination. So we need another addressing mechanism in a connectionless internet network, the link layer addresses of the two nodes. A link layer address is sometimes called a link address, or sometimes a physical address, and sometimes a MAC address. So we cannot simply have IP addresses, because IP addresses are dynamic in nature, whereas MAC address, we need something more static to communicate reliably between two nodes in an internet network. So since a link is controlled at the data link layer, the addresses need to belong to the data link layer. When a datagram passes from the network layer to the data link layer, the datagram will be encapsulated in a frame, and the two data link addresses are added to the frame header. So, apart from the IP addresses, the two MAC addresses also have to be provided. So, since a link is controlled at the data link layer, so the addresses need to belong to the data link layer, and this is how it is formed. So we have three links in this router. We have three links and two routers. So we have two hosts, Alice and Bob. Alice is the source and Bob is the destination. For each host, we have shown two addresses, the IP addresses and the link layer addresses. So N is the IP address and L is the link layer address. So first we will encapsulate the host IP address and host IP address and source IP address, and then we will give the link layer address of the host. We don't know the link layer address of the destination, so we will give the IP address of the source and destination, but the link layer address of only the source and the nearest network device that is available for routing. So we have each frame carries the same datagram with the same source and destination, so the datagram is not changing. The datagram has N1 and N8, which are the link layer addresses. So sorry, which are the IP addresses of the source and destination, and that is not changing, because if that changes, then the source and destination address change. Whereas the link layer addresses change according to the network route. So we for each host we have shown two IP addresses, and we have shown three frames. Each frame carries the same datagram, but the link layer addresses of the frame change from link to link. In link 1, the link layer addresses are L1 and L2. So in link 1, it is connecting the source to the nearest network device, so it's L1 and L2. But once it reaches this link, it will go to the next router. So here the link layer address will change to L2 and L3, whereas from there it will change to L3 and L4, then L4 and L5, then L5 and L6, then L6 and L7, then finally at this link device it will be L7 to L8. So at router there is L1 to L2 incoming, it will be changed to L3 to L2, and then from there L3 to L4. So a link device only does one change, whereas a router will do two changes, because first it will receive, then it will store in a buffer, and then it will reroute it according to the destination address routing table. So there are three types of addresses. One is a unicast address. Each host or each interface is assigned a unicast address. Unicasting means one-to-one communication. So unicast address is assigned to every link and every host. And for one-to-one communication, unicast address is used. For one-to-many communication, so there is multicast address. Multicast address has one-to-many, so the device can transmit to many devices. So then there is, after multicast, there is a broadcast. Broadcast means one-to-all communication. So if a particular device uses its multicast or broadcast address, then it can connect to multiple or all devices at once. Now there is address resolution protocol. Address resolution protocol's main task is to resolve conflicts between addresses. So anytime a node has an IP datagram to send to another node, it has the IP address of the receiving node. The source's host knows the IP address of the default router. Each router except the last one in the path gets the IP address of the next router by using its forwarding table. So all the next IP addresses are always got by forwarding table. So there is a routing table stored at each router, which which can know where to send the packet next based on the destination. The last router knows the IP address of the destination host. However, the IP address of the next node is not helpful in moving a frame through a link. We need the link layer address of the next node. So IP address of the next node is not helpful because reaching that next node may not be straightforward and you might have to take a longer route. For one-to-one straight short connection, you need a link layer address. So to know the link layer address, we have to use the address resolution protocol or ARP. The ARP protocol is one of the auxiliary protocols defined in network layer. It belongs to network layer. ARP accepts an IP address from an IP protocol, maps the address to the corresponding link layer address, and passes it to the data link layer. So the main job of ARP is to ARP maps. So anytime a anytime a host or a router needs to find the link layer address of the another host or router in its network, it sends a ARP request packet. The packet includes the link layer and IP address of the sender and the IP address of the receiver. Because the sender does not know the link layer address of the receiver, the query is broadcast over the link using the link layer broadcast address, which we discussed. So there is a link layer broadcast address. So because the link layer unicast address is not known, so instead using the broadcast address, you reach to the device, you reach out to the device. Because the broadcast address is publicly accessible. Every host or router on the network receives and processes the ARP request packet, but only the intended recipient recognizes its IP address and sends back an ARP response packet. The response packet contains the recipient's IP address and link layer address. This packet is unicast directly to the node that send the request packet. So what you do is you take the ARP can be summarized as take the IP address of sender receiver and link layer address of the sender to get back the link layer address of the receiver. Rx is equal to link layer address of Rx is equal to ARP of sender IP, Rx IP, sender LL. But how does this ARP response reach? It reaches via the broadcast packet. So taking the sender IP, receiver and IP and the sender link layer address, it broadcasts the ARP request packet to all the devices in the network that it is connected to. But only one of them responds with the ARP response packet, and that ARP response packet contains its link layer. So link layer address of the receiver will be ARP of these three. Now once you have received the link layer address, then you can send to the next layer, the next network device. Once that next network device receives the packet, it will again do a ARP request and get the link layer address of the next device. So we use broadcast for link layer address packet, and once we have received back the link layer address, then we do a unicast to that particular link layer address. So this is address resolution protocol. Now we'll go to DHCP. Now we come to DHCP, or Dynamic Host Configuration Protocol. So we have seen that a large organization can receive a block of addresses. So here first we need to talk about addresses, of course. So we have talked about IP addresses. The first IP address that is probably used is IPv4. So a protocol like IPv4 has an address space of 2 to the power 32. So it is 32 bits. So it has a IP address of 2 to the power 32, which is 4.2 billion. So if there were no restrictions, then 4 billion devices would be connected to the internet. But the IP addresses do not have, the IPv4 does not have 4 billion devices. So IP addresses have four parts. So four numbers like 128.11.3.31. Now we have classes in addresses, because previously now we have classless addresses, but previously we had classes in these addresses. There were hierarchy. So this hierarchy is decided by this network length and correction length. So a 32-bit IPv4 addresses is divided into two parts. One is called the prefix, which defines the network, and another is called the suffix, which defines the particular device in that network. So prefix defines the network that it is in, while suffix defines the particular device that is the part of that network. So the prefix length is n bits and suffix length is 32 minus n bits. Now based on the length of this n, there are classes of addresses. So there are three fixed length prefixes, which are n equal to 8, n equal to 16, and n equal to 24. And based on that, the address space was divided into 5 classes, or called class A, B, C, D, and E. So this is known as classful addressing. So in class A, the network length was 8 bit. So we have 8 bits, but for the first bit was 0, will define the class. So for the first bit defined that it was a class A address. So instead we had 7 bits for network identifier. So for class A there can only be 128 networks. Because the prefix length is small, so we have a huge suffix length. So because we have a huge suffix length, we can accommodate a very large number of devices. But even if we can have 128, but there can only be 128 groups or 128 networks that can have a class A address. So class A address is used for very, very large organizations which have a huge number of devices connected to it. But this class A addresses has become obsolete. And then there is class B. The class B, the network length is 16 bits, but the first 2 bits are class identifier. So we have 14 bits as network identifier. So there are 16,384. And in class C, there are 2 million networks. Class D is not divided. It is a multicast address, and class E is reserved for future use. So like that. But the classful address has become obsolete nowadays. No one uses classful addresses really, because they were not distributed properly, and as a result we have we have like class A addresses which were very, very large, and so most of the addresses, so if you assign someone class A address, they can connect 16 million devices, but very few organizations have even 1/100th of 16 million devices. So this remains uh, unused. A lot of addresses remain unused in class A. Whereas as you go down in class C, we have a different block. That is, the network is so small that only 256 devices. We can have a large number of networks, but as we go down in class, the number of networks increases, but the number of devices per network decreases. So in class C, we have a different problem altogether, that because the number of networks is very large, so everyone can have their own network, but they can connect at most 256 devices, not more than that. So that is the problem with class C. And so this classful addressing was done for. So to alleviate this address depletion, two strategies were proposed. One is subnetting, another is supernetting. In subnetting, a class A or class B block in subnetting, a class A or class B block is divided into several subnets. Each subnet has a larger prefix length. So we divide this class A into subclasses, and then with larger prefixes they can accommodate a smaller number of devices, but they will have larger number of subnets. So instead, now that subnetting and now in class A, because we have very large networks, so the subnetting was used, whereas in class B or class C, in rather class C, we had a problem of very very small networks, individual networks, but a very large number of networks. So we use supernetting. In supernetting, large number of networks were merged to form one mega network, and this created a larger block than 256, so to attract more organizations. But ultimately this was given away because of the address depletion problem, that is, we could not sufficiently give allocate addresses to IP, allocate addresses to all devices, as the large number of devices grew exponentially really. So instead we have classless addresses. In classless addressing, we have basically blocks, and these blocks are assigned to networks. So these blocks belong to no one but are randomly assigned, and then based on these blocks, these IP addresses assigns its clients. So the client, they are assigned blocks, the IP addresses are assigned blocks, and then they give those blocks to client. Now in class, but we have to know which part of IP address is prefix, which part is suffix. So we introduce slash notation, because now there is no fixed class identifier. So instead we have variable length blocks. So we have to know where the network identification stops and where the device identification starts, because we have to identify the network as well as the device which is part of that network. So we have a slash notation. In this slash notation, the prefix length is specified. So slash n, IP address slash n means the prefix is 8 or 12 or 25 or something. So in this way we can identify separate. So if you write this 12.24.76.8 into bits, then the first 8 bits will be the network, the next 24 bits will be the device identifier. Whereas here, if you write it in decimal, the first 25 bits will be network identifier. So it is a very small network, but it will have 25 and then rest 7 bits. So it will have at most 128 devices, because 2 to the power 7 equal to 128. Now we will go to some problems. So the first question is that which field in IPv4 address is used for error detection? Checksum. Checksum is used. Time to live gives you the packet duration, whereas protocol gives you the protocol with which the packet is handled, and identification is used to identify fragments if fragmentation is done on the packet. So the correct answer is checksum. Next, in IPv4, the service type of the service in the header field, the first 3 bits are called type of service. So precedence bits, sync bits, code bits. So the first 3 bits are called in the type of service bit. So the whole field is called the types of our service, 1 byte. Out of that, the first 3 bits are called the precedence bits. Next, your router has the following IP address on Ethernet 0, that is the default Ethernet connection, 172.16.2.1. So which of the following is a valid host ID? /20. So the first 23 bits, here you have 172.16.2.1, 172.16.2.1. So you have to convert this to binary. You can just use calculator here. Programmer's calculator. So 172 is in binary 1010 1100. So it is equivalent to 10101100. Next, dot 16 is 000010. Four. No, sorry. Yeah. So this is 60. 2 is 00000010, and 1 is 00000001. Now you remove the dot. So you see 23 bits slash 23, I think. Slash 23. Let me check once. Yeah, it's slash 23. So 23 of these bits. So 23 means 8, 8, and then 7 up to this. This is the network identifier or prefix. So this identifies the network. And what is the host ID? The host ID is the first of this. So the first address of this, the node IDs. So these are the node IDs. Node ID. So the first node ID 0000, all zeros before the last one is 1. So 1 decimal. That is node ID. So here you see the, if you see that the host ID here the IP address already is 00001 for node ID. That is, this is already the host. So this is the host. So the host address is actually 172.1.16.2.1. So this is the host. So D. So the correct answer is D. None of these, because 172.16.2.1 is the host ID. Next, consider the following statements about ARP. So the ARP is protocol is used to get MAC destination MAC address from the destination IP address. The ARP protocol is used to get destination MAC address from destination IP, or the ARP protocol is used to get destination IP from destination MAC, or the ARP stands for address resolution protocol. So destination MAC, the thing is, ARP is used to get the link layer address or the MAC address from the known IP address. So B is given in the reverse order. We don't get the IP address from the MAC address. Rather, we get the MAC address from the IP address. So A is correct, B is incorrect. And C, ARP does stand for address resolution protocol. So A is correct, B is incorrect, C is correct. So only B is incorrect. So the correct option is D. D for Delhi. Next, an ARP request is a broadcast. So it broadcasts to all the links and ARP request. So then the ARP response will be unicast. So it broadcasts ARP to, so it's basically asking that I want to send to this particular IP address, who can send my packet to this IP address, and one device will respond that I can send this packet to the requested IP address, and then there will be a unicast ARP response. State whether true or false. The inverse ARP protocol is used to get the IP address from the MAC address. So yeah, if ARP is used to get MAC from IP address, then inverse ARP will be used to get IP from MAC. So it is true. Next, what is the default subnet mask of class B? So class B has 16-bit prefix. So a mask is something in which all the bits are 1. So it has a 16-bit prefix. So the prefix will be for class B. Mask is prefix is 16-bit, so 16-bit prefix, all ones. So there will be 16 ones. 8, 9, 10, 11, 12, 13, 14, 15, 16. Next, there will be all zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So if you separate decimal separate by 8, so you have the default sub mask for class B as 255.255.0.0. So correct answer is B. Option B for Bombay. So what is the maximum number of IP addresses that can be assigned to a host on a local subnet that uses 255, 255, 255, 224? So mask, subnet mask. So here the first 3 bytes are off. First 3 bytes are all on. So you only have the 224. So 224, if 224 is the if 224 is the IP address, then if 224 is the mask, then 224 is basically the 0th address. The mask is the 0th address. So after that, how many you can go till 255 to 255? So from 224, if you go till 255, you will get 30 hosts, 30 addresses. So the correct answer is 30. So there can only be 30 IP addresses. Next, so these two will not be possible right now. So we will end here only based on today's class. And this was the last problem solving session for this NPTEL course. So there will be no more NPTEL problem solving session for this communication network course. So yeah, this is the last class. Thank you. Bye.